Hi, my name is Tiffany, and today I'm going to be talking about our work in using machine learning models to characterize and predict the engagement patterns of over 4,000 blind and low vision users of an audio-based navigation app. Audio-based navigation technologies use audio cues to help people who are blind or have low vision navigate more independently and confidently. So in this work, to get a wider scale understanding of how people who are blind or have low vision actually engage with navigation technology in their everyday lives, we analyzed user activity logs of Microsoft Soundscape, a mobile app. Unlike step-by-step navigation apps, Soundscape uses a user's location and activity to provide 3D descriptive audio cues that enhance ambient awareness and provide more context about an environment. Among other capabilities, users can hear spatialized audio callouts as they pass various intersections and landmarks, they can navigate to and save particular destinations, and they can preview locations of interest by simulating navigation to the location via audio. We had access to app activity data logs of 4,725 blind and low vision users. These users all began using the app between January and June of 2021 and come from over 60 countries and regions. Using this data, we wanted to use machine learning to determine whether the first week of use can predict long-term retention. We formalized this task as a binary classification task. Given a set of engagement features from the user's first week of app usage, can we predict whether the user will return again? To extract app engagement features from unstructured data logs, we developed a novel feature taxonomy that combines individual user and app usage features into 16 groups comprising a total of 106 features. An example of a feature group is retention features, which consists of usage time and consistency of use in the first week. Another feature group was callout experiences, which comprises the frequency and types of audio location callouts that the user experiences. We trained the model on the engagement features and then analyzed the resulting classifier's ability to predict user retention, as well as engagement features that were most informative of longer-term retention. Our classifier model achieves an F1 score of 0.741 and an accuracy of 0.761 in predicting user retention after the first week, outperforming both baselines. This indicates that the model picked up on some patterns in app usage that may be unique to blind and low vision users. To get a better sense of which features were the biggest indicators of long-term retention, we identified the features that were most consistently selected by our model in predicting future usage. We identified two major types of features that were important: general usage metrics and exploration-related features within the first week. For general usage metrics, people who use the app longer in their first use experience and more often in their first week tend to return again. People who tended to return to the app also had more exploration-related usage of the app. They had more engagement with audio location callouts and more use of the app in a background state. This indicates use of the app to explore ambient surroundings during user journeys rather than active route planning that involves active button clicks or typing. And users who returned to the app tended to use the virtual street previewing functionality more, perhaps in exploring new locations and increasing their navigational independence. In conclusion, this work leverages machine learning to better understand and characterize the interactions of blind and low vision users with mobile navigation technology on a larger scale. Future work can combine our insights with qualitative usability studies in order to design more effective interventions and more context-aware navigation technologies, and to evaluate longer-term mobile app engagement of blind and low vision users.